In this video, we're going to add a few more useful circuits to your toolkit by teaching you how to take sums and differences with operational amplifiers, as well as generating offsets. So far, we've seen how op-amps can make voltages bigger, but we haven't tackled a common and important application. In the circuit shown on the left, our teensy pin is trying to measure a zero-centered signal. And a zero-centered signal could come from a lot of things. Piezos are a great example. However, we have a problem because the teensy pin is referenced to ground, and it can't measure negative signals. So we're losing some of the information from our sensor. In this video, we're trying to see if there's some op-amp we could stick in between the signal and our teensy pin to offset the voltage so that it could be measured. So for instance, if we were to add 1 volt to it, this signal would work just fine being measured by our teensy pin. An op-amp circuit that can do this 1 volt offset trick and shift a voltage upward exists. And I've drawn a related circuit on the side of this slide. In particular, this circuit is a general case adder and subtractor, which will allow you to shift voltages up and down and to add them and subtract them from each other. Now, this circuit looks like a mess to analyze, and it is, but there's a reason we're doing it. The strategy for this video is to solve a really useful general case, and then use the results of the general case on some common circuits. I'm going to analyze this circuit to get the general results, but this derivation isn't the most important part of the video, even though it's going to take a little bit of time. Once we're done with the derivation, we'll use it to give you some really cool circuits that you can take into the lab. All that said, this circuit isn't too bad and you can totally figure it out based on what you already know. I encourage you to try it yourself if you want a little brain teaser, or at minimum, take close notes and follow this process so that you can tackle other tricky op-amp circuits you find in the wild. Remember that one of the main goals for this lecture set is for you to be able to analyze any op-amp circuit that you come across by applying these op-amp rules. Before we start, I want to chat about the naming conventions. RF has that subscript because it's in feedback. RG goes to ground. All of the RN resistors are attached to the negative input of the op-amp, and all of the RP resistors are attached to the positive input. As usual, we're going to try to find V- and V+, then set them equal to each other. We're going to start finding V- by writing current balance at the V- node using nodal equations. So Vn3 minus V- over Rn3 represents the current through Rn3. Similarly, Vn2 minus V- over Rn2 represents the current through Rn2. The sum of the currents coming into the node through Rn1, Rn2, and Rn3 has to be equal to the current leaving the node through Rf, which gives us this first equation. We rearrange this by putting all the V- terms on the right side. Notice that this leaves us with a scaled sum of all the Vn terms on the left side. That's promising given that I've said we're going to get an amplifier that adds voltages at the end of this. This big term on the right side almost looks like a parallel combination, even though it's not raised to the power of -1 like a parallel group usually is. So we're going to group it together and call it 1 over R parallel n. Finally, we clear R parallel n by multiplying it to the other side. We can do all this same stuff to isolate V+. So we start with a nodal equation at the V+ node. Note that the current flows through RG to ground, which makes this a little easier than the V- side. Then we collect terms and define R parallel P, and then finally cross-multiply again. With all this done, the next step is to set V+ and V- equal to each other. I've pulled the V+ and V- equations from the previous slide so that we can set them equal. Equating them is pretty painless, though we wind up with a lot of terms. Then we isolate V out on one side of the equation, and finally we multiply by Rf over R parallel n to clear and isolate V out. This leaves an R parallel P over R parallel n coefficient in front of each of our Vp terms, so I've factored that out to make the whole thing easier to remember. Each input voltage is individually weighted by Rf over the source resistance, and all of the Vp terms have an additional gain of R parallel P over R parallel n. So, whew, we're done. We now have a general summing equation, and there are a lot of variables in it. Further, a lot of them are coupled. You can use this for design, but it takes some diligent attention or computer assistance. However, it does do what it says on the tin. This amplifier adds up weighted versions of all of the Vp voltages and subtracts off weighted versions of all of the Vn voltages. We could extend this analysis to as many or as a few resistors as we wanted, so if you have the occasion to add 8 voltages together, then you already have the math and the circuit design to get the job done. But we actually want to go the other way with this general equation and use it to analyze much smaller circuits. The circuit that's pictured here is called an offset amplifier, technically an offset inverting amplifier, and it is super useful. You're going to use it all over E80, so it's worth keeping track of this analysis and especially the result. The circuit is small enough that you could just do normal op-amp analysis to it. You can find V+ and V- and equate them. But we just went to the trouble of deriving this thing, so let's put it to use. The first thing we should note is that the offset amplifier is missing a bunch of stuff that was present in our general equation. RP2 and RP3 are infinitely big, and VP3 and VP2 are 0, so we can get rid of those terms. Same's true for Vn2 and Vn3, which means that we already have something that looks better. This looks like the gain of a normal inverting amplifier, minus RF over Rn1, plus some offset term, which depends on Vp1. So we take the output of an inverting amplifier and shift it up to a higher voltage. This is exactly what we were looking for in the first slide of this video, so great! We can actually take a few more steps to make calculating the offset really easy. These steps involve picking apart the offset coefficient. We expand out R parallel P and divide things through to discover that we're left with an expression that looks like a voltage divider between Rg and Rp1, applied to Vp1. Now, if we look at our circuit, we can see that this divider expression is exactly reflective of this divider over here. So the output of that divider gives us the voltage in the middle here, which is just V+. That means we can replace this kind of complicated term with just the value of V+. We can play a similar trick with R parallel N and RF. If we expand R parallel N, which is smaller than RF because resistors in parallel are always smaller than the resistors that make up the combination, then we can cancel some terms and wind up with a simple expression here. We can substitute these two simplifications back into our equation and wind up with a really simple expression for the offset amplifier. Remember it, it's useful. I've put up another circuit here that's a good opportunity for you to practice with the sum and difference equation. You guys should pause the video and take a crack at this application. You can apply the master summing and differencing formula to it, and I've included it here for convenience. Notice that all the resistors in this circuit have the same value, even though I've given them different labels so that the figure seems familiar. Alright, so pause the video now, give it a shot. So the first step to getting the answer is to recognize that we don't need any of the Vp terms because the positive input of the op-amp is just directly grounded. The second is to recognize that all the resistor values cancel out so that you just have simple addition. This trick, by the way, works for the general adder subtractor too. If you use the same resistor values in that circuit, then you wind up just adding all of the P voltages and subtracting all of the N voltages, because it makes all the weighting factors equal to 1. This circuit is called a summing amplifier. Technically, it's an inverting summing amplifier, and it's a good way to stitch together weird-looking signals from multiple sources. So in conclusion, you can use op-amps to add and subtract voltages, which you'll often want to do to make sure that they stay inside of your voltage rails. There's a general adder-subtractor op-amp structure and formula, which I've included on this page. And offset amplifiers are really useful, and you're going to use them all over E80. I've included that formula here too.